Well, yesterday was easy. You learned all of the rules of programming in Lisp, almost all of them. And so at this point, you're now certified programmers, it says. However, I suppose what we did is we sort of got you a little bit into an easy state. Here you still believe it's possible, that this might be programming in BASIC or Pascal with just a funny syntax. Today, that illusion, or you can no longer support that belief. What we're going to do today is going to completely smash that. So, let's start out by writing a few programs on the blackboard that have a lot in common with each other. What we're going to do is try to make some abstractions that are not ones that are easy to make in most languages. We'll start with some very simple ones that you can make in most languages. Supposing I want to write the mathematical expression which adds up a bunch of integers. So if I wanted to write down, say, the sum from I equal A to B of I. Now you know that's an easy thing to compute a closed form for, and I'm not interested in that, but I'm going to write a program that adds up those integers. Okay? Well, that's rather easy to do. To say, I will define the sum of the integers from A to B to be, well, it's the following two possibilities. If A is greater than B, well then there's nothing to be done and the answer is 0. Okay, and this is how you're going to have to think recursively. I'm going to say, if I have an easy case that I know the answer to, just write it down. Otherwise, I'm going to try to reduce this problem to a simpler problem, and maybe in this case I'm going to make a sub-problem of the simpler problem and then do something to the result. So the easiest way to do this is say that I'm going to add the index, which in this case is A, to the result of adding up the integers from A plus 1 to B. Now, at this point, you should have no trouble looking at such a definition. Indeed, coming up with such a thing might be a little hard, the synthesis, but being able to read it at this point should be easy. And what it says to you is, well, here is the sub-problem I'm going to solve. I'm going to try to add up the integers one fewer integer than I added up for the whole problem. I'm adding up the one fewer one, and that sub-problem, once I've solved it, I'm going to add A to that, okay, and that will be the answer to this problem. And in the simplest case, I don't have to do any work. Now, I'm also going to write down another simple one just like this, which is the mathematical expression, the sum of the squares from I equal A to B. And again, very simple program. And indeed, it starts the same way. If A is greater than B, then the answer is 0. And of course, we're beginning to see that there's something wrong with me writing this down again. Okay? It's the same program. It's the sum of the square of A and the sum of the squares of the increment and B. Now, if you look at these things, these programs are almost identical. Okay? There's not much to distinguish them. They have the same first clause of the conditional, and the same predicate and the same consequent, and the alternatives are very similar too. They only differ by the fact that whereas here I have A, here I have the square of A. The only other difference, but this one is sort of unessential, is that the name of this procedure is SUMINT, whereas the name of this procedure is sum square. So the things that vary between these two are very small. Now, whenever you see yourself writing the same thing down more than once, there's something wrong and you shouldn't be doing it. And the reason is not because it's a waste of time to write something down more than once. It's because there's some idea here, a very simple idea, which has to do with the sigma notation. Right? It's this much. Not depending upon what it is I'm adding up. And I would like to be able to always, whenever trying to make complicated systems and understand them, it's crucial to divide the things up into as many pieces as I can, each of which I understand separately. I would like to understand the way of adding things up independently of what it is I'm adding up, so that I can use that having debugged it once, having understood it once, and being able to share that among many different uses of it. Here we have another example. Okay, if I want, this is Leibniz's formula for finding pi over 8. It's a funny, ugly mess. What is it? Something like 1 over 1 times 3 plus 1 over 5 times 7 plus 1 over 9 times 11 plus, and for some reason, things like this tend to have interesting values like pi over 8. But what do we see here? It's the same program, or almost the same program. It's a sum. Okay, so we're seeing the sigma notation, although over here we're dealing with incrementing by 4, so it's a slightly different problem, which means that over here I have to change a by 4, as you see right over here. It's not by 1. Okay. The other thing, of course, is that the thing that's represented by square in the previous sum of squares, or a, when I'm adding up the integers, well, here I have a different thing I'm adding up, a different term, which is 1 over a times a plus 2. But the rest of this program is identical. Well, anytime we have a bunch of things like this that are identical, we're going to have to come up with some sort of abstraction to cover them. You think about this, what you've learned so far is the rules of some language, some primitives, some means of combination, almost all of them, the means of abstraction, almost all of them. But what you haven't learned is common patterns of usage. Now, most of the time you learn idioms when learning a language, which are common patterns that mean things that are useful to know at a flash. And if you build up a great number of them, if you're a Fortran programmer, of course, everybody knows how to, what do you do? For example, to get an integer, which is the biggest integer in something. Okay, it's a classic thing. Every Fortran programmer knows how to do that. And if you don't know that, you're in real hot water, because it takes a long time to think it out. However, one of the things you can do in this language that we're showing you is not only should you know something like that, but you give the knowledge of that a name. And so that's what we're going to be going after right now. Okay, well, let's see what these things have in common. Okay, right over here, we have what appears to be a general pattern. A general pattern which covers all of the cases we've seen so far. There is a sum procedure which is being defined. It has two arguments which are a lower bound and an upper bound. The lower bound is tested to be greater than the upper bound, and if it is greater, then the result is 0. Otherwise, we're going to do something to the lower bound, which is the index of the computation, and add that result to the result of calling the procedure recursively on the lower bound incremented by some next operation, okay, with the same upper bound as I had before. So this is a general pattern, and what I'd like to do is be able to name this general pattern a bit. Well, that's sort of easy, because one of the things I'm going to do right now is there's nothing very special about numbers. Numbers are just one kind of data. It seems to me perfectly reasonable to give all sorts of names to all kinds of data. For example, procedures. And now many languages allow you to have procedural arguments, and right now we're going to talk about procedural arguments. It's very easy to deal with, and shortly we'll do some remarkable things that are not like procedural arguments. So here we'll define our sigma notation. This is called sum, and it takes a term, okay, and A, a nexter, and B as arguments. So it takes 4 arguments. And there was nothing particularly special about me writing this in lowercase. I hope that it doesn't confuse you, so I'll write it in uppercase right now. The machine doesn't care. But these 2 arguments are different. These are not numbers. These are going to be procedures for computing something given a number. Term will be a procedure which, when given an index, will produce the value of the term for that index. Next, which will be given an index, will produce the next index. This will be used for counting. And it's just very simple. It's exactly what you see. If A is greater than B, then the result is 0. Otherwise, it's the sum of term applied to A and the sum of term, the next index, let me write it this way. Now, I'd like you to see something, first of all. I was writing here and I ran out of space. What I did is I started indenting, according to the pretty printing rule, which says that I align all of the arguments of the procedure so that I can see which ones go together. And this is just something I do automatically, and I want you to learn how to do that too, so your programs can be read and understood. However, what do we have here? We have 4 arguments. The procedure, the lower index, lower bound index, the way to get the next index, and the upper bound. What's passed along on the recursive call is indeed the same procedure, because I'm going to need it again. Okay? The next index, which is using the next procedure to compute it. The procedure for computing next, which I also have to have separately, and that's different. The procedure for computing next is different from the next index, which is the result of using next on the last index. And I also have to pass along the upper bound. So this captures both of these and the other nice program that we were playing with. So using this, we can write down the original programs as instances of sum, very simply. A and B. Well, I'm going to need an identity procedure here because the sum of the integers requires me to, in this case, compute a term for every integer, but the term procedure doesn't want to do anything to that integer. So the identity procedure on A is A, or X or whatever, and I want to say the sum of using identity as the term procedure and using A as the initial index and the incrementer being the way to get the next index and B being the high bound, the upper bound. This procedure does exactly the same as the sum of the integers over here. Computes the same answer. Now, one thing you should see, of course, is that there's nothing very special over here about what I used as the formal parameter. I could have, for example, written this x. And it doesn't matter. I just wanted you to see that this name does not conflict with this one at all. It's an internal name. For the second procedure here, the sum of the squares, it's even a little bit easier. And what do we have to do? Nothing more than add up the squares. I mean, this is the procedure that each index will be given. Will be given to each yes. Each index will have this done to it to get the term. Okay, that's the thing that maps against term over here. Then I have A as the lower bound, the incrementer as the next term method, and B as the upper bound. And finally, just for the thing that we did about pi sums are sort of, well, it's even easier to think about them this way, because I don't have to think. What I'm doing is separating the thing I'm adding up from the method of doing the addition. And so we have here, for example, pi sum AB. Well, it's a sum of things. I'm going to write the term procedure here explicitly without giving it a name. Okay, this is anonymously. I don't necessarily have to give a name to something if I just want to use it once. And of course, I can write sort of an expression that produces a procedure. I'm going to write lambda, the Greek lambda letter here instead of lambda in general to avoid taking up a lot of space on blackboards. But unfortunately, we don't have lambda keys on our keyboards. Maybe we can convince our friends in the computer industry that this is important. Lambda of I, it's the quotient of 1 and the product of I and the sum of I2. Starting at A, with the way of incrementing being that procedure of an index I, which adds I to 4, and B being the upper bound. So we can see that this notation, the invention of the procedure that takes a procedural argument, allows us to compress a lot of these procedures into one thing. This procedure, sum, covers a whole bunch of ideas. Now, just why is this important? I tried to say before that it helps us divide a problem into two pieces, and indeed it does. For example, if someone came up with a different way of implementing this, which of course one might. Here's, for example, an iterative implementation of sum. Okay. Iterative implementation, for some reasons, might be better than the recursive implementation. Okay. But the important thing is it's different. Now, supposing I had written my programs this way, that you see on the blackboard on the left. That's correct. The left. Okay. Well, then, if I want to change the method of addition, then I would have to change each of these. Whereas, if I write them like this, that you see here, then the method by which I did the addition is encapsulated in the procedure sum. That decomposition allows me to independently change one part of the program and improve it, perhaps, without changing the other part that was written for some other cases. Thank you. Are there any questions? Yes, sir.
Go over next thing and next thing else.
Yes, it's the same problem. I'm sure you're going to have to work on this. This is hard. And the first time you've ever seen something like this. What I have here is procedures can be named by variables. Procedures are not special. Actually, sum square is a variable which has gotten a value, which is a procedure. This is define sum squared to be lambda of A and B something. Right? So the procedures can be named. Therefore, they can be passed from one to another, one procedure to another, as arguments. What we're doing here is we're passing the procedure term as an argument to sum, just so that we get it around in the next recursion. Here we're passing next as the procedure next as an argument also. However, here we're using the procedure next. That's what the parentheses mean. We're applying next to A to get the next value of A. If you look at what next is mapped against, you see, remember that the way you think about this is that you substitute the arguments for the formal parameters in the body. That's what, if you're ever confused, think of things that way. Well, over here, in the sum of the integers, I substitute identity for term, okay, and 1 plus the incrementer for next in the body. Well, the identity procedure on A is what I get here. Identity is being passed along. And here I have increment, 1 plus, being applied to A. And 1 plus is being passed along. Does that clarify the situation?
We could also define explicitly those two functions.
Oh, yes.
And pass them.
Sure. We could pass. What we could do is we could have given names to them, just like I did here. In fact, I gave you various ways so you could see it, a variety. I mean, here I defined a thing, which I passed the name of. I referenced it by its name. Okay, but the thing was, in fact, that procedure of one argument x, which is x. Okay, the identity procedure is just lambda of x, x. Okay, and that's what you're seeing here. Here I happen to just write its canonical name there for you to see. Okay. Suppose we take our 5-minute break?